Didi Akin-Lee, a trainee clinical scientist in the National Health Service, explained in the previous video clip how he uses vector mathematics to analyse a patient's walking motion in terms of angles. In this next example, he looks at the forces involved in walking.
So here we have the same 2D example that we used before. And in this particular instance, our subject has stepped onto a force plate. Now this force plate goes from here, the origin at 0, and comes across a distance a to this point over here. At the corners of the force plate, we have a number of force measurements that are fed directly into our computer. So at each of these corners in this 2D example, that is here and here, we have a vertical force measured, Fy1 here, and a horizontal force, Fx1. And over here we have Fx2 and Fy2. And of course, we don't know if these vectors are going up or down, but those are things that come out in measurements. So what we want to find in this particular situation is the point at which our subject is applying pressure onto the ground. We consider this reaction vector that occurs due to our downward pressure on the ground. As we push against the ground, it pushes back.
So in this situation, there are 3 forces to consider. The force measured at the left-hand edge of the force plate, F1, the force measured at the right-hand edge, F2, and the force from the ground reacting to the subject's forward motion, R. Didi's first step is to calculate the distance x. Note that in the diagram, Didi has shown all the forces acting in an upward direction, but the result of the analysis will indicate their true directions. It is convenient to break these forces down into horizontal and vertical components. Now there are 2 sorts of equilibrium to consider. Firstly, there is static equilibrium. The plate is moving neither horizontally nor vertically, so the forces in the vertical direction, for instance, must balance out. Similarly, there is rotational equilibrium, as the plate is not rotating. Taking moments about the origin O, Didi writes a second equation involving Fy2 and Ry. The goal is to compute the distance x, which can be obtained by combining these 2 equations, eliminating Ry.
So the reason we need to work out the location of this centre of pressure is this is really important when you consider the effects that that force has on each of the joints.
Didi now has all the information needed to compute the tension of the muscle in the knee.
So at this stage, we know what our ground reaction vector is, we know its magnitude, and we also know its location. And from our kinematic data, we know exactly where the joints of our subject's leg are at this particular moment in time. And what we can start to do from this point is to build up a picture of the kinds of forces that the subject's muscles are exerting as they're walking in this particular way. So in this case here, we've got the ground reaction force pointing backwards to just behind the knee, and we're going to look at the moment that that exerts around the knee. It's a very simple calculation. From the location of the knee and from this, the location of the force vector, we can work out this perpendicular distance in here, which I'm going to call A, little a, and that's the moment arm of the force around the knee. What I'm going to do here is just look at one particular muscle and see how it tends to act in this situation. So the quadriceps are up here, and the tendon stretches round the knee. They go around the kneecap and attach at some point onto the shin over here. And we can say that the force exerted by the quadriceps on the knee, just over the kneecap, and comes off, say, in this direction. So we're going to call this force the tension in the quads. We know that at the kneecap we've got a particular moment arm in here. I'm going to call that B.
Again, consideration of rotational equilibrium results in a simple relationship between R, A, TQ and B, leading to a result for the tension in the quadriceps, TQ.
You can test that out yourself. If you were to bend your knees down, you can feel that your quads are active, and we require this force to stop us from collapsing to the ground. So this is actually a very oversimplified view of looking at how the muscles act as we're walking. But there's a lot of research going into actually understanding what's going on in our bodies. This gives us an indication, but it's not the whole picture.